I've been interested in what is it like to be an observer? Why do I care about that? I care about that because in our physics project, it's become an essential thing to understand what we're like as observers, because it seems to be the case that what we're like as observers determines what laws of physics we perceive there to be. So it becomes important to be able to characterize what are we like as observers, because if we were observers that are different from the way we are, we would perceive, I think, laws of physics that are different from the laws of physics that we perceive. So in fact, I think in the end, the picture is going to be that the laws of physics are what they are because we are observers of the kind we are. So that's a kind of a different, it's sort of a reframing of thinking about what does it mean to have a fundamental theory of physics. It's a theory of physics that is the theory that has to be the way it is for observers like us. It couldn't be the case that you could kind of wheel in another theory, that, God could have invented a different theory of the universe. For observers like us, it is, I think, inevitable that the laws of physics are the way that they are. So, okay, so how do we understand what is an observer like us?
Right. So what is an observer like us?
So first we have to kind of ask, what is an observer doing? The world's a complicated place. We have finite minds. The goal of us as observers is to take the complexity of the world and kind of find a way to stuff it into our finite minds. And in a sense, what that's doing is it's saying there are lots of details in the world, but they're not going to fit in our finite minds. We somehow have to compress what we're seeing in the outside world so that it fits in our finite minds. Another way to think about it is we've got to make equivalences between different kinds of things. Like I'm sitting here staring at this camera in the retina of my eyes, there are all kinds of photons falling that are kind of making some elaborate pattern there. But all that my brain is perceiving is, there's this object in front of me. So I'm doing many equivalences, and what I extract from this sort of the raw physicality of what's going on is something that there are many different arrangements of photons that would lead me to perceive the same thing. And what you realize is that's a common feature not only of us human observers, but all the measuring devices we use and all these kinds of things. It's all about, there are lots of details in the world. We just want to measure a particular thing. So a quintessential example would be, you've got a gas, it's got a bunch of molecules bouncing around, you're trying to measure the pressure of the gas. How do you do it? Well, maybe you just have a piston on the side of the box, and you say, how hard is the piston pushed by the molecules in the box? Mm-hmm. And there are all kinds of different configurations of molecules hitting the piston, and they go this way and that way and the other. But all that matters in measuring the pressure is what the aggregate force on the piston is. So there are all these different configurations of molecules that we equivalence together to deduce that one thing that we care about, which is the force on the piston. And so I think as we think about ourselves, the fundamental feature of an observer is we're doing lots of equivalencing. We are taking many different states of the world and saying, we don't care about the differences between these things. We're just going to extract this sort of essence of what's going on. And that's what we as an observer are thinking about. Now, it's sort of interesting to see when we imagine kind of a computational process going on, we're always generating fresh states of the world. We're going from one state of the world, we compute the next state of the world, the next one, and so on. We're always sort of generating fresh states of the world. On the other hand, when we are being observers, we're sort of doing the opposite. Instead of generating fresh states of the world, we're trying to equivalence together lots of states of the world. We're trying to say there are lots of things which we might think of, which in some sense are different, but we're going to treat them for our purposes as equivalent. Now, you might say, how could you deduce anything interesting from knowing about these kinds of equivalences? It turns out that the notion of these kinds of equivalences is critical to sort of deducing what we can think of as physical laws. Because in some sense, a physical law is an attempt to explain some aspect of the universe in a way that we can understand with our minds. I mean, we could say about the universe, it just does what it does, and it has all these little things going around in it. But we don't have any narrative explanation of what's happening. The kind of the nature of physical laws is we want to take what the universe does and we want to somehow get a description of it that sort of fits in our minds. And so, for example, when it comes to something like, I don't know, a gas with a bunch of molecules bouncing around, the thing that fits in our minds is some aggregate description that talks about pressure and temperature and things like this, not the detailed motions of those molecules. So for us, we're talking about the gas laws. For the system underneath, it's got all these molecules bouncing around. It's important that we are only able to talk about things at the level of the gas laws, because if we could talk about things at the level of molecules, we'd come to quite different conclusions about what's happening in the world. So this is essential to, for example, the second law of thermodynamics. Because what does the second law of thermodynamics say? It basically says things tend to get more random over time. What's the application of that? You know, if you take some mechanical motion, you're sort of pushing something backwards and forwards. Well, that's a very systematic motion of atoms in the thing, but that systematic motion tends to get sort of ground down into random motion of molecules that we call heat. And once you have things as heat, it's hard to get them back into systematic motion. You don't find that all those molecules that are randomly bouncing around suddenly line themselves up and start systematically pushing the block of wood or whatever it is. So there's this tendency for things to get more random. But from the point of view of the individual molecules, that's not what's going on. From the point of view of the individual molecules, they're just following certain laws of motion. You could even reverse those laws of motion if you wanted to. The molecules are just doing definite things. It's only from the point of view of observers like us, with our kind of bounded computational capabilities, that we say we don't know how to follow all of those details. For us, what the molecules are doing should just be considered random, and all we should be able to deduce is something about their average properties, like their average temperature, their average pressure, whatever else. So the fact that we believe that the second law of thermodynamics is right, or that the gas laws are right, is a consequence of the fact that we are observers of the kind we are. If we were observers who routinely traced every motion of every molecule, we would say, what do you mean that there's randomness in what's going on? There's no randomness. I can see what every individual molecule does. So in a sense, that's an example of a place where being an observer of the kind we are is the thing that causes us to perceive laws of the kind we perceive. If we were an observer who followed every molecule, could do every computation to figure out what would happen with every molecular motion, we wouldn't say, oh, it's just random, you can only look at the averages. We would be sort of concentrating on the details of what was happening at the level of molecules. So that's an example. And by the way, the same exact thing seems to happen in space-time and in quantum mechanics. And the thing that for me is like spectacular, realization is, in 20th century physics, there were three big theories: general relativity, the theory of gravity, the theory of space-time, quantum mechanics, and essentially statistical mechanics, whose sort of prize exhibit is the second law of thermodynamics, the theory of how systems of very large numbers of components work. Those three basic kind of achievements of 20th century physics, I think one had thought that maybe the second law of thermodynamics was derivable from something lower level. Maybe just from the laws of mechanics, and some mathematics, you could deduce the second law of thermodynamics. People had thought that in the 1800s. They were kind of, by the early 1900s, they were kind of giving up on that idea, and it was just like a mystery that was left hanging out there. But there was some thought that the second law might be somehow derivable from something sort of more fundamental and already known. For general relativity and quantum mechanics, that really hadn't been the thought. The thought had been, at least as the way I always thought of it, is we just happen to get those laws of physics. The universe we live in just, for reasons we don't understand, happens to have those particular laws of physics. Well, I think we can say more than that now. I think we can say, and it's really surprising that we can say this, but I think we can, that all three of those kind of achievements are consequences of the fact that we are observers of the kind we are. That it is inevitable that we have to perceive the physical world to have those particular laws because we are observers like we are. If we were different kinds of observers, we would observe different physical laws. but we observe those laws because we're observers like we are. Now, okay, there's more to say about how this all works, but the kind of the thing that I was trying to do with sort of my efforts in observer theory is to characterize something about what observers are. It's all about these equivalence things. It's all about taking the complexity of the world and sort of stuffing it in a finite mind by equivalencing many different states of the world to say all we care about are these features. That's one side of it. And then being able to see kind of how you flow through from what characteristics do observers like us really have? And by the way, many of those characteristics are things so obvious to us that we've never really called them out as things that we actually should say, yes, this is a feature of us. So an example, which turns out to be really important, is we believe we're persistent in time. We believe that we have a thread of experience that goes from the past to the future, and it's still us. Well, really, in our models of physics, for example, at every moment in time, we're made of different atoms of space. And so in some sense, it's always a different us at every successive moment. But it's but somehow we have the perception that we have this continuous thread of experience, something that seems very, very obvious to us, but is nevertheless an assumption. It's not obvious that we would have a consistent thread of experience. We could imagine being some kind of, alien intelligence that was different at every moment. It was like, like we have successive generations of humans, and each one has its own separate experience. We could imagine that was somehow compressed. It's very hard to think it through what it would be like to be in that situation where we don't have any sort of memory for ourselves. I don't really know how it will work. That's kind of a science fiction type scenario that would be interesting to think through. But the fact that we believe we have this persistent, unique thread of experience for each of us is non-trivial. It could also be the case that we could, instead of experiencing things in a single thread, there could be multiple threads. We could have, one could sort of imagine what it would be like to have sort of multiple consciousnesses in the same brain, so to speak.
Would you be able to imagine what that's like, or is it part and parcel of you being the kind of observer that you are that you can't even imagine it?
I think it's really hard to imagine. I've been trying to imagine a bunch of these things. I mean, I think it's sort of a very interesting challenge to imagine sort of what it would be like to be an intelligence very alien compared to us. And, I made some attempts along those lines, actually. And I would say it made a little bit of progress. But I would say that's a really difficult thing to wrap one's brain around. I mean, I think one of the things, this is sort of a side point, but, I've been, mostly familiar with kind of the Western tradition of thinking about things and philosophy and so on. And, I've been curious because people have been telling me for years, the things you're doing resonate with various kinds of Eastern philosophies and so on. And I've been curious to try to understand how that works. And, my initial investigations say, yes, there are things there that sound an awful lot like things that I've long been talking about, so to speak. But it's really hard for me to, even at that very small distance, it's pretty hard for me to get sort of an internal feeling of what it's like to think about things in terms of, let's say, Eastern philosophy. And, it feels like the kind of thing where it's sort of a strange thing. The way we think about things is built on this sort of tower of experience. And it's like you can just jump out into the kind of uncharted universe of possibilities. And it's quite disorienting and quite non-human. I mean, in a sense, this is something I've done for the last 40 years or something, is investigating what I would now call ruleology, the behavior of just arbitrary, simple sets of rules. So, you just write down some computational rules, you start running them, you see what happens, you get all this elaborate, complicated behavior. The question is, can you humanize that? Can you kind of give a human narrative for what's going on? And it can be really difficult. it's kind of like, well, that vaguely looks like a this or that, but it is, it is a definite rule. It is a possible sort of law of physics for some kind of artificial physics. And do I have a kind of a human way to describe it? No, not necessarily. But in order to get to the point where you have sort of a human way to describe it, you end up having to have this sort of tower of civilizational development. Like, okay, there's this weird pattern. Do we have a word for that? If we had a word for that, I'd be able to say, yes, remember that, the squiggle-do pattern, and I'd know what I was talking about and you'd know what I was talking about. But without having without our civilization having reached that point in, as I would call it, rulal space, without us having reached that point, we haven't colonized it. We haven't said, we're going to put down, we're going to call this the city of whatever. We're going to put a word down here for this. And once we have that, and we all have kind of a common experience of that, then we can start talking about it. But without that, it's really hard to have, it's really hard to, both for us to talk about it, and even for me to do a good job of forming thoughts about it. Because I think, when we form thoughts about things, the way that we, our words and language and so on seem pretty important to us forming thoughts. I mean, they're the way that we concretize our process of thinking. I mean, the way I see it these days, and this is again a sort of a side point to the main things we were talking about, but this whole question about sort of how do we communicate a thought? Something that there's something going on inside our brains. It's a bunch of electrical firings or whatever else, but those electrical firings somehow add up to something abstract, a thought. And, my electrical firings are going to be different from your electrical firings. How do we package up a thought that corresponds to some electrical firings in my brain? How do we package it up, send it to your brain, have it unpack, and have it correspond to something like the same thought? And I think that's kind of the role of concepts, which we sort of concretize in words and human languages and things. We pack it up into a concept. A concept is a robust thing. It's a cat, for example. And then, I can transport that concept to your brain. You can unpack it, and you might have a similar view of what I'm talking about as the one that I internally have. And I think that in one very bizarre kind of way of thinking about things, this is now jumping around a bit, but when we think about space-time and we think about particles like electrons and so on, what is an electron? An electron is a lump of existence that is somehow unchanged by motion through space. There's an electron here that it moves, and it's the same electron in some sense. It is transporting through space and time its electronness. Its existence is being transported, in some sense, unchanged through space and time. Even though in our models of physics, that electron is made of different atoms of space. As it moves through space, it's made of different atoms of space. It's kind of like, the eddy in the fluid, where the eddy is moving around, although it's made from different atoms at different moments in time. And so I think this notion of concepts is a concept is kind of like a particle, but not in physical space, but in what I call rulal space. And minds are like exist at different places in rulal space. And so when we use concepts to sort of exchange thoughts, it's like sending a particle from one place in rulal space to another. And we have this
Could you reverse that? Sorry, could you reverse that and then also say that instead of a concept being like a particle is like a concept, and the universe is talking to itself and exchanging ideas, and that's what we see as physics?
Yes, you probably could. I mean, it's kind of like it resonates a bit with kind of the universe as the thoughts of God actualized, so to speak, which is sort of a popular Spinoza type theological view of the universe. Yes, I think that's in a sense, the sort of the idea that what the universe is doing is like thinking is kind of this thing that sort of, it's all computation, so to speak. I've had this idea I've talked about for decades, the principle of computational equivalence, The idea that sort of you can think about all processes as computations. Not only are they computations, they're also computations of somehow equivalent sophistication. So the computations that are going on in our brains that we interpret as thinking are the same level of sophistication of computations as are happening in the universe, where we're interpreting what's going on as physics, for example.
If you enjoyed this toe clipping, then the full video is linked in the description. Don't forget to follow Theories of Everything with Curt Jaimungal on Spotify for exclusive content and in-depth discussions. Your support on Spotify helps us grow and to reach more curious minds like yours. Check out the link in the description and join the Core Toe community on Spotify today. See you there.